Hello everyone and welcome to this video. So this is the first in a series of some calculus exam questions. The question we're going to be doing today is 2014 question 9. So it's a nice long question for calculus, mainly differentiation. And what you'll see a lot of the time with calculus is there'll be kind of 2 to 3 questions on the exam. 1 or 2 will be short questions, and then there's generally a long question or part of a long question as well. So it takes up a lot of the paper 1 course, and it's definitely something we have to be very good at before going into the exam. So with that, we'll get started. So as I said, this is 2014 question 9. So what you'll see with the 2014s is there's kind of, it's when the start of the project maths was coming in. I think it was 2015. So, and then there's kind of some sample questions as well. So like there's a 2014, I think, sample as well. So this one is taken from the actual SEC exam. So we have, it's a long question, as I said. So anything kind of above, generally question 7, 8, and 9 are long questions. So Kieran is preparing food for his baby and must use cooled boiled water. We have an equation, so we can see it is a exponential equation and describes how the boiled water cools. In this equation, what we have is we have T is time in minutes when the water is boiled. Y is the difference between the water temperature and the room temperature at time T measured in degrees Celsius. A and K are constants. So what we're basically told is that both T and Y are variables. So we know Y is kind of our output, or kind of our end result, and T is going to be our input variable. So T is our independent and Y is dependent. A and K are constants. So the kind of things to take into account is T is in minutes. So if they tell us, let's say, an hour, we have to put T as 60. And Y is the difference between water temperature and room temperature. So that's important as well, the difference. So the temperature of the water when it is boiled is 70 degrees Celsius, and the room temperature is a constant at 22 degrees Celsius. So write down the value of the temperature difference Y when the water boils and find the value of A. So what we're basically saying is, because we're told that T is time from when the water is boiled. So this is kind of in this question, it's kind of what we assume is that T is now equal to 0. So it's kind of like a hypothetical, straight away as that water has just been boiled and we stop the clock. So time is 0 minutes. So basically what we have is, so we can say at T equals 0, Y is going to be equal to the difference between 100 and 23, which is 77 degrees Celsius. So here is 77 degrees Celsius. Now we need to find A. Well, we know that Y is equal to 77, and that equals A multiplied by E by K, where T is 0. So now what we need to know about this is that we know that any number multiplied by 0 is just 0. So that's the same as saying 77 is equal to A e to the power of 0. And we know that any number to the power of 0 is 1. So that's A. So 77 is A. So that's nice and easy. So our equation for Y is now going to be equal to 77 E KT. So that wasn't really tricky. The kind of main trick was realizing that T is equal to 0, because in the question, what we basically, when they're told that, like, when the water is boiled, we just assume that time is equal to 0, because it basically is. So there might be a couple of seconds pass between the time the kettle boils, and let's say you pick up the water, but that doesn't matter. It's as soon as the kettle boils, so time is equal to 0. So that's just things you have to see. It doesn't tell you explicitly time is 0, so use T is equal to 0, but we have to think for ourselves and say, okay, if the water is just after boiling and T is the amount of minutes after the water is boiled, well then obviously T is 0. So that's something we kind of have to get used to. They're not going to tell us because we're high level maths, we have to kind of figure it out. So After 5 minutes, the temperature of the water is 88 degrees Celsius. So we have to find the value of K correct to 3 significant figures. So, what we now need to do is, so we have T is equal to 5. So Y is going to be equal to, so the water temperature is 88, and we were told that the room temperature is a constant 23, so Y is going to be equal to 65 degrees Celsius. So using our formula from above, or 77 EKT, we can say 65 is equal to 77 e to the power of k multiplied by 5. So now we want to find k, so that's going to require us, now remember we've kind of done it in sequence and series sometimes and financial maths, and we do it in calculus a lot as well. Whenever we have an index as a variable, we're going to be using logs basically. So that's something we have to bear in mind. So whenever we see something like this, a variable as an index, we're going to be using logs. So what we always want to do, we want to isolate our variable. So we're going to have to move all the constants over first. So if I'm multiplying by 77, I'm going to be dividing on the other side. So 65 divided by 77 is E and then 5k. Now, we want to get the log of E, so if it was 20 to the power of 5k, we'd want to get the log of 20. So in this case, we want to get the log of E, and we know that the log of E is equal to ln, the log of the natural number. So we have to do ln on both sides. And we always know that whenever we have the log of the same, this is going to cancel out this, and we're just going to be left with 5k. So basically what happens is, what's basically happening is we have 5k ln by e. So if you look at your log tables and look at the rules of logs and the rules of indices, what you'll see is any, so if you've L of n to, let's say, 5 squared, that's the same as 2 ln 5. So that's what we're doing here. So what's happening is these aren't essentially cancelling out. What happens is we get 5k multiplied by ln e, and then the ln e will just be 1, so we're left with 5k. But I just like to say that they cancel out because it just, for me, it just makes it easier. I don't have to go on a long speech. It's kind of easy to understand. So what we're basically left with now is just ln of 65 over 77. So if we put that into a calculator, we get minus 0.169. So 3 significant figures. I'll just do 4 for now, equals 5k. So we can say therefore k, or we won't do therefore yet. So we'll say k equals minus 0.1694 divided by 5, because if we're multiplying, we have to divide both sides by 5. And then what we get is minus 0.0339. So this is my final answer. K equals minus 0.0339. So what we're basically getting at here is the 3 significant figures. What that means is that the first time you hit a number that isn't 0 is your first significant figure. So we kind of neglect this, and our significant figures are these, so 3, 3, and 9. So that's something to keep in mind. It didn't say, if it said 3 decimal places, then you do 0.034, but because it says 3 significant figures, we're kind of only interested in when we first hit a number that isn't 0, if that makes sense. So that wasn't too tricky. It's once you kind of get the hang of the logs, and if you get the log to the same base, then these questions become very easy. So Kieran prepares the food for his baby when the water was cooled to 50 degrees Celsius. How long does it take, correct to the nearest minute, for the water to cool to this temperature? So we now know that y is equal to 77 e to the power of minus 0.0339 t. So we now know that y is equal to 50 minus room temperature, so y is 27. So it's very similar to the question we did already, but because we already know what k is, the k variable, we now need to do the log to get what t is. So the exact same process, 27 over 77 equals e, and this. Then we get the log of the natural number. So very similar. And we're then left with ln of 27 over 77 is minus minus 1.04797, and that equals my minus 0.0339 t. So t equals this divided by that, and if you put that into a calculator, what you get is 30.91. So therefore, to the closest minute, t equals 31 minutes. So again, nice straightforward question. Once you know that the log, once you know that once we have a variable as a index, we get the log of the base, which that's the base e, so ln, and then it brings basically the variable back down as just a standard number down here. So once you did that, you actually were able to do these two fairly easy. So you're probably talking 10 marks for A, 10 marks for B, 10 marks for C, something like that. So now we're told, using your values for A and K, sketch a graph ft equals AEKT, blah, blah, blah. So we know that we always use y and f of x interchangeably because x is usually your independent variable. But in this case, t is our independent variable, so we have f of t. So it's the same thing as y. And that equals 77 e to the power of minus 0.0339 t. So if I just zoom out slightly, we have this graph here. So we have y is for the difference in temperature and t is time. So we know that. So what we can do is, let's say, go up in intervals of 20. So just make a small table. Say 0, 20, 40, 60, 80, 100. And then just so we can have our x values and our y values. So 0, 20, 40, 60, 80, and 100. So we know that when t was 0, we had 77. So we have 77. Then if you put it in for 20, what we get is 39. So it's 39.1. Then you get 28 or 27.8. Then we get 20 or 19.8, 14. Oh, sorry. I was doing that wrong. So I was going up in intervals of 10. 39, 20, 10, 5, and 3. So we can see that it kind of jumps considerably, the first and second one, and then gets smaller and smaller, the difference between them. So we can just mark these little points. So we have, let's say, 77 there, then 20, 39, around here. Then 40 goes up to 20. 60 goes up to 10. 80 goes up to 5. And then 100 goes to 3. So my sketch probably won't be fantastic, but it would look something like, so it's not going to be a straight line. So something like this. Or if I do it slightly better, so you can see that there's definitely a curve in it. And there's barely any difference between 80 and 100. So there's only 2 degrees. Right at the first 20 minutes, it drops by 38 degrees. So there's a huge difference at the beginning and only small differences at the end. So that's simple as that. Probably another 10 marks there. So on the same diagram, sketch a curve GT equals AEMT. So it's hard to see, but that says M. Showing the water cooling at a faster rate, where A is the value from part A above, and M is just a normal constant. So we still have our 77E, but it's MT. So we're going to want show the water cooling at a faster rate. So let's say at 20, as opposed to it being, what was it, 37 degrees, we want it at, let's say, 20 degrees. So if we wanted something like that, so let's do 20 equals 77 EMT, and we did our 20 divided by 77, so the log of that, and the log of EM by, so this is 20 as well, so then you'd be left with the natural log, so ln of 20 divided by 77, and that's minus 1.35 equals 20m. So m is going to equal to that divided by 20, which is minus 0.067. So if we said m was something like that, then we could basically sketch this graph and do the exact same. So I've basically done, as you can see, part I suggests the possible value for m for the sketch you've drawn and give a reason for your choice. So really all I need to do is, we don't even need to do that up here, we can do it down below, but let's say we just pick something like this. Let's say we pick green. So it would still be at 0, it would still be 78 degrees, but it would just be dropping much quicker. So we can see it like that. And now it wouldn't have to go exactly at 5, but let's say it went to, let's say 4 or something, or 4.5, it would look exactly like that. So that's dropping at a quicker rate, and we can see that m is more negative than our minus 0.0339. So that's kind of more negative than this, for example. So all I'm really going to do is I'm just going to rewrite what we did there. So suggest one possible value for m. So you could say m equals, let's say, minus 0.067, and then we could do all that again. 20 equals 77 EM20, and then you can have ln of 20 over 77 equals ln of EM20. So left with 20m equals minus 1.35, then therefore m equals minus 0.067. And that's your answer. for that. Nothing too tricky there really. I'll just get rid of this up above. And then you could actually investigate that this will lead to the water cooling faster. We can put, now I don't have loads of space here, but you could do 77 e to the minus 0.0339 t is greater than, or 77 e to the power of minus 0.067 t. So I don't have enough space there. And then if we actually go through this, kind of using, again, the same thing, so the two 77s will end up cancelling each other out, and you're left with this is greater than that, then you get the log of both sides, and then you'd be left with minus 0.0339 t is greater than minus 0.067 t. So then our t's can cancel out because we know that t has to be greater than 1, let's say, and we have the two negative signs. So if we want to change these to a positive, so again, we're going to want 0.0339 t, and then whenever we change the signs, we have to change the inequality to 0.067 t. So the t's can just basically cancel each other out because t has to be greater or equal to 0, and 0.0339 is less than 0.067. So therefore, true. So this is greater than that. So therefore, the water is going to be cooling quicker. And that's kind of how you'd show how this will, or how, let's say, this g of t, so don't forget it's called g of t, is going to cool quicker than f of t. Okay, so now moving on from that, what we're going to be looking at is these two questions. So again, we're still doing the 60 marker. We want to find the rates of change, so that's important, of the function f of t, so that was the original function, at 1 minute and after 10 minutes. So give your answer correct to 2 decimal places. So we know that f of t is equal to 77 e minus 0.0339 t. So whenever we want to get the rate of change of a function, we always do f of t, or f dash t, to show integration, or sorry, to show differentiation. And we can see that on page 25 of the log tables, that whenever we have e to the power of ax and we differentiate it, it becomes e to the ax. So what's happening is we get minus, so whatever the constant is, or the coefficient of the t, now in this case it's x, but obviously we're dealing with t, goes down the bottom. So minus 0.0339 multiplied by 77e, and then this stays the same, minus 0.0339 t. So now if we multiply all that, we get minus 2.6103 e to the power of minus 0.0339 t. So perfect. Now we're going to substitute in 1 for t, so t equals 1 and t equals 10. So minus 2.6103 e, we keep going by 1, and then minus 2.6103 e to this. By 10 minutes, what we get is minus 2.52, so we can see it's a negative slope, minus 1.86. And then we get these answers, 2 negative slopes. This is more negative than that, so basically, as we know from our graph in the last page, that that the drop from, let's say, 1 minute to 10 minutes is a lot steeper than, let's say, 10 minutes to 20 minutes. And if you looked at the graph at t is 90, it would be really, really small again, so like minus 0 point something. So that's just kind of all it's showing us, is the rate at which we change. So showed that the rate of change of ft will always increase over time. So we know that whenever we want to show it's always increasing over time, we're going to have to look at the kind of, I like to call it double differentiation. So we're now looking at f with 2 dashes and t. So that's basically differentiation of the differentiation. So if we were to get f double dash of, and our equation was, so we had minus 2.6103 e minus 0.0339 t. Then following on for that, what we'd get is, again, this goes down to here. So we're now left with minus 2.6103 e to the power of minus 0.0339 t. And then we're going to multiply it by minus 0.0339. And what we end up getting is 0.0885 e to the power of minus 0.339 t. So we have a positive number here, which is good. So we can basically say is that this is positive, and this has to be positive, because so e is basically always a positive number, and when we have the negative, we know that's basically 1 divided by e to the power of 0.0339 t. So 1 divided by a positive number is still going to be positive. So that means that it's always increasing over time. So we can make that look a bit nicer. We can change it to 0.0885 divided by e to the power 0.0339 t. And then we can just say, therefore, f double dash t is greater than 0 for all t. And the rate of change will always increase. The rate of change for f of t will always increase. So that's 60 out of 60 marks for this question. As you can see, it's not very tricky. So calculus is tricky in general, so the questions they ask aren't as, let's say, tough English-wise, but the actual doing of the work is tricky. So like, okay, A wasn't too bad. The main trick was seeing that t was equal to 0. Then this part here, part B, we just put t is for 5 minutes, and we already had the value for y, so we could just sub everything in and then get our second variable. And then C was basically just putting in a value for y and getting t, so a lot of it was actually very similar. Then moving over to the second page, doing the first graph was easy enough. All it was is putting in values into a table, and then basically just copying that into the graph. Then this bit is slightly tricky because it's kind of like, okay, how do I actually show that my sketch does actually show water cooling at a faster rate? And then we did it this way. So we said, because basically this number is a greater number than that, then the water will cool quicker. And then here, we just have to get kind of our buzzwords, or know our buzzwords. We know that rate of change is the same as saying the slope of, which is the same as saying differentiate. And then down in part double I, we just had to double differentiate. And again, it's kind of like a buzzword. It showed that the rate of change will always be positive over time. And because our double differentiation was a number greater than 0, it means that we're increasing. So that's it for this question. It was a long enough question, but again, it was the first of 3 long questions, let's say for paper 1, so they're always going to be a bit longer. They're 60 minutes, so you basically have about 25 minutes to do the whole question. So I think we did it in about that. So thanks everyone for watching. I hope this kind of made a bit of sense. It's always good to put the theory back into practice, and there'll be a few more videos for calculus because it's a very big topic on paper 1. So thanks for watching. Goodbye.